All right, folks, a very warm welcome to our Support Vectors weekly paper reading session. The topic today is differential transformers. This topic is a very interesting topic in the sense that it goes to the way attention in transformers are defined. It leads to some surprising results. The idea that they use is quite simple and beautiful, actually, quite insightful. And the authors show that in benchmarks, it gives substantively better results than the classic transformer attention. So we are going to go through this paper in a careful way. The authors of this paper, they are from Microsoft Research and Tsinghua University. And with that, it just came out in October. So it's a fairly recent paper. And let's get started with this paper immediately. So we'll do a few things. First of all, what is this paper about? What is it that they're proposing, this differential transformer? Why do we need it? How does it work? And then we'll see that the results are quite impressive. And then we'll reflect upon why it works. Like, why does such a simple idea prove to be so very effective? So let's start with the abstract. The main point is that they do, which they mention in the first line, is that transformers tend to allocate attention to irrelevant context. So what it means in simple terms is that let me say that if you look at the attention score, which is your K, Q, the dot product between the K and the Q, with obviously the normalizing factors, which I might gloss over and not mention. When you do, let me just put it away. Attention score, let me just call it the score function, is the softmax of this. And of course, the attention is essentially the score function times the value. And given the input, it gets decomposed into K, Q, V, as we know, WK, WQ, WV. Through these transformations, the input embeddings are scattered into three different embeddings, the KQV. The query is sort of the context. It searches for how much attention it needs to pay to each of the other tokens or the value of the other token. And that is your attention vector. So that's your basic transformer as attention, the self-attention as we know it. Now, in the very first line, the point that they're mentioning is they tend to over-allocate attention to irrelevant context while canceling noise. Specifically, the differential attention mechanism calculates attention scores as the difference between two separate solutions, a softmax attention maps. So in the next sentence, they propose a solution. But before they propose a solution, let's zoom in and see what is it that they're talking about. What they are saying is, suppose you have a query token, Q, and it is, you want to see how much attention it is paying to something that is really what you want it to pay attention to. And Rai, please keep an eye on the people in the meeting room, in the waiting room.
Yeah, I'm on it. I'm accepting them.
So if we look at this picture, you notice that the answer, so I mean, obviously you have deliberately handpicked an answer that should get more attention. When you look at the amount of normalized attention, so this is your normalized attention score, your softmax. 0.03 is certainly bigger than the other tokens. But those other tokens, if you look at the cumulative attention that they end up getting, this part and this part, their values are more than that of the answer. So they coin a word which they call attention noise. It is the cumulative attention paid to those tokens in the input, which are, or in the context window, which are essentially irrelevant to the query. And cumulatively, as you can see, about 0.34 plus 0.18, that amounts to a lot of that, 0.52, I suppose. Quite a bit of attention is going to that, whereas the attention that is given to the actual answer is very small. As this paper is going to argue, especially through results, it will show that if you use a slightly different mechanism, a way to boost up the signal to noise ratio, then it leads to dramatically better downstream task performances. The question is how? So let's go up and read this. So the first sentence, therefore, now makes sense. Transformer tends to allocate attention to irrelevant context, as we saw. In this work, we introduce diff transformer, which amplifies attention to the relevant context while cancelling noise. Specifically, the differential attention mechanism calculates attention score as the difference between two separate softmax attention maps. So this is the how part of it. I would just mark it as how. So while this part is the problem, this is the how of the solution that they are proposing, the authors are proposing. The saying is the subtraction, because it's the difference between two quantities, the subtraction cancels noise, promoting the emergence of sparse attention patterns. And that is the crucial thing. They say that if you do this, then what happens is that it cancels the noise. And why does it cancel the noise? We will deal with in a later way. And it has to do with gradient flow, how the gradient of the backpropagation, during backpropagation, how does the gradient flows of the loss function. So experimental results on language modeling show that diff transformer outperforms transformer in various settings of scaling up model size and training tokens. So it's a validity statement that this approach works. But more intriguingly, it offers notable advantage in practical applications, such as long context modeling, that is very long context or inputs, I believe, a key information retrieval, that is retrieving the key bit of information from a long input, hallucination, mitigation. How do you mitigate hallucination? As you know, hallucination is a significant nuisance for LLM in many situations. Unless you're doing creative writing or poetry, in many situations, you don't want the machine to hallucinate. You want it to be factually correct. So anything that mitigates hallucination is, of course, a welcome thing. In context learning, which is that better learning from the information in the prompt, and reduction of activation outliers. So quite a few advantages if you look at it. So there is, just to highlight it, again, I'll just say that long context modeling, of course, it's able to handle much longer context windows, information retrieval, and these things will become obvious that they happen, hallucination mitigation, and most interestingly, a reduction of activation outliers. This is important because one of the things that traditionally happens is that in the traditional transformer, because of the nature of the softmax, what happens is that, and this is how softmax works, especially in the presence of very long context windows, that some particular, in the activation, you'll suddenly see some very few peaks, and then all of this will be small activations. But you'll suddenly see these giant peaks, outlier values. So these are the activation outliers, and you tend to not sort of like it after you start seeing this. We will see that all of these are helped. By being less distracted by irrelevant context, diff transformer can mitigate hallucination in question answering and text summarization. For in-context learning, diff transformers not only enhance accuracy, but is also more robust to order permutation, which was considered. So this is actually a pretty big point, and they might as well have mentioned it in the first list itself. One of the problems that happens with LLMs, as you know, is that if you give it a list of facts or examples, especially in few short learning, then its performance is unfortunately sensitive to the order in which the exemplars are mentioned. You change the order of the exemplars and the performance of your prompt and therefore the LLM goes up or down, right? So it's very sensitive to it. And that sensitivity is obviously not a good thing. What you would want is you're giving the same information and order shouldn't matter. So you want your system, your LLM, to broadly be robust to the ordering or permutational changes of the exemplars. That's an important point. And it's actually quite interesting that on this front, it achieves quite a bit of remarkable results, as we will see in this paper. So obviously, with all of these advantages, the last point they mentioned is quite convincing. The results position Diff Transformer as a highly effective and promising architecture to advance large language models. So that's a summary claim that this paper makes, the authors of this paper make. Right, so let's go through this paper carefully. Now, first of all, before we understand how it does it, let's look at the results because this figure 1 speaks for itself. This is the figure on the left is the traditional transformer, the traditional attention head. Transformer. This one is their innovation. And as you can see, the answer stands out quite dramatically, and you can see the noise suppression. So they give an analogy in this paper, which is quite apt. They say that if you're used to differential amplifiers in electrical circuitry, something like, if my recollection is right, which is something like this amplifier, X1, X2, right? So what happens is that this amplifier just amplifies the delta between these two, X1 and X2, right? So this is a differential amplifier. So any kind of noise, any kind of a noise that is there in both of them, they will get canceled out, right? Because it's only looking at the delta between them and amplifying it. So some analogy from electrical engineering is it behaves like a differential amplifier. Or another way they mention, which is sort of like a noise cancellation headset. In a noise cancellation headset, you take, of course, the noise signal, and then you basically invert its phase. And so you remove it, you filter it out. So these are obviously sort of analogies rather than very strict equivalences, but be as it is. The other thing is, the third topic that they mention is multi-needle retrieval. What is multi-needle retrieval? What you do, suppose you have a very long piece of text and you ask a question, the answer is in there somewhere in one line. It's like a needle you have put in a haystack. The job of the LLM is to, given the query, find that needle, because that needle is that crucial sentence or phrase or couple of sentences that contains the answer to the question. Right? So one of the benchmarks or ways of evaluating an LLM has been to see the performance of LLM in multi-needle retrieval. You hide a few needles, a few text, a few pieces of information. Some of them are really the answer to the query, and some of them are deliberately misleading or noise, right? Distractions that you inject into the text. And then you see how well or how accurately your LLM is able to pick out the correct needle from the haystack, right? If you have an analogy of your whole text input is that it's a haystack with a lot of things that are quite irrelevant, right? And even distracting facts. So when you look at the performance improvement, this is this is very, very dramatic shift if this is true. I mean, if this validates itself out more generally, I would imagine that this is a pretty huge delta in accuracy. You're saying that for the multi-needle retrieval benchmark, you have practically a 30% gain in accuracy. Now, 30% gain in accuracy is quite substantive. So let's see how is it that they achieve it. And with that, I won't read every paragraph as usual. I will sort of focus on the key topics. Right? So we already talked about the attention noise, so we won't go to it. So, and we will go straight to the differential transformer. Well, how does it work? So what they do, the best way to look at it is through this picture. And this picture and this code essentially is most of the implementation. So what they are doing is an input X, instead of just producing one set of key and query pairs, it produces two sets of key and query pairs. So for example, so X goes in K1, Q1, and K2, Q2 sets, and then of course V, right? So what it means, therefore, is that you are doing something like this. K1 is W1 KX, K2 is W2 KX, then Q1 is W1 Q X. I'm using this familiar notation in transformers. And again, these are, so there are 5 such matrices and, sorry, X. So instead of 3 matrices, traditionally you have just the K, the WK, WQ, WV. Here you have 2 sets of K, W, WKs and 2 sets of WQs. That is the main thing. And so what will happen is, if you think about it, the implementation wise, what you will have is, you will have one score, let me call it S1, and that will be equal to the softmax of K1, Q1, the inner product, over square root of D, if you remember. And this one will be the softmax of K2, Q2, square root of D. And I'm just writing the formulas down as it is. And as you know, so from this we derive that attention 1 is S1 V1, attention 2 would be basically S2, sorry, V. V is common to both. V. And what they are saying is, we are going to take the difference of the two attentions. The final attention is A1 and up to a proportionality constant, A2. This time, this, right, times V. Right? So it is like S1 minus lambda times S2 in my notation times this. And we can see this in the code. Let's look at this code a little carefully. This makes sense. So you have a WQ matrix, which is twice as long now, because it is actually going to produce 2 different Q1 and Q2s. This also, yeah, that's why you have the split. And V remains the same. The V is the as before. No change to this. And so now this, oh, by the way, they use this square root of D as the 1 over square root of D as a scaling factor. And in there, actually, maybe I should not have used S1. I should have said score 1. Let me just say so that the two notations don't conflict. Score 1, score 2. So this is the scaling factor, 1 over square root of D. Now, observe that this is nothing but Q1.Q2, Q1.K1, Q2.K1. And what are you returning? We are returning literally this. Attention is basically, actually, I should call it, score. This is nothing but score 1 minus lambda score 2. Well, let me call score, I should use score. Two times V, right? Which is what they're doing. So this is the minus lambda dot product with V. So this is your basic attention, differential attention. The rest of it more or less remains the same. Multi-head just means you concatenate many of them, and then you multiply, you do a dot product with a WO, as we are used to doing in the traditional transformer. No new changes. All right, so with that being there, now, which is what you see, the X goes into one channel and another channel. So it becomes a difference between two softmax. Then the normal things, group norm and etc., takes place. Some bit of mechanics take place. But this is the core idea. Now, the question is, if you do it like that, and they go right away, and so they do mention a little bit of other things. For example, based on Llama, the recent work on Llama, the activation function that they bring in is the sweet glue, which is swish this times this. So there's a bit of literature on why this is a pretty good idea. There's been papers in Llama 3.2 or 3.1. They used it, RMS norm, normalization, layer normalization, etc. These are expected things that you would expect. Now, right away, they say that this is how we do it. And if you do it, this is what happens. So when we look at the results, and one thing I found interesting is that they don't go, at least in the main part of the paper, till you read the appendix, you don't quite get a clue why did it work. And we will get a chance to think about why such a simple change has what seems to be significant results. But the results are quite significant. So here we are. If you take so what they do is they make sure that the architecture they create is flops compatible with the traditional architecture. It isn't that because it has two different softmax computes. One can argue that, well, you know what, you're doing literally twice as many computations in the attention. So they compensate for it by just halving the number of layers, attention head layers, right? So that the overall parameter count and the overall computes remain the same. So it's a pretty fair comparison. And what they show is that compared to the benchmark, so let's take any one benchmark, you notice that everywhere, in fact, throughout, it seems to be achieving pretty state-of-the-art results. Right? Then, when you do this graph, and this is something that's quite interesting. If you scale the model with the number of parameters, like you take models of different parameter counts, 3 billion, 2 billion, 7 billion, whatever it is, and so forth, a number of parameters, this is in billion scale parameter. So from 1 to 10 billion parameters, I suppose. What you notice is, and they mention what are those individual sizes, scale model size, 1.4, 2.8, 6.8, and 13.1. Right? These are the four model sizes they take. What you notice is that the loss function for the diff transformer, consistently at every size, the loss is less than that of the regular transformer. So that is interesting observation, and that gap in performance remains consistently true. Likewise, when you look at the number of tokens to train, it turns out that you can train this machine, the diff transformer, with about 36% less tokens. Right? So that's an interesting result. that you need a smaller model. So for example, if you look at this, it is using almost 40% less parameters. Nevertheless, it's able to achieve pretty good results. Also, if you increase the context length, as you know, LLMs have a difficulty handling long sequence lengths, right? So here, they are looking at the cumulative average negative log likelihood. So as you know, the LLM's loss function is the negative log likelihood. So they are computing it cumulatively over different sequence lengths. And what they find again is that the diff transformer does better. Now, this picture is a little bit, it's a bit dense. So this picture needs a lot of explaining. So let me explain that. And for that, we'll read this key information retrieval paragraph. It says that the needle in a haystack test is widely used to evaluate the ability to extract critical information embedded in a large context. Large context, we just give it a very big input. We follow multi-needle evaluation protocol of blah and blah. The needles are inserted into varying depths within context of different length. So each needle consists of a concise statement that assigns a unique magic number to a specific city. So think of a city, San Francisco, and you can say 15. Right? The goal is to retrieve the magic number corresponding to the query cities. So the LLM, or the way you evaluate the LLM is you say, what is the magic number for San Francisco? And then you see whether it is able to find the answer. Now, as we know, one of the issues with LLM has always been that their performances are if the answer is in the beginning or the middle or 3/4 of the way there or in the end, LLMs are sensitive to that. Right? For example, in general, RNNs, for example, if the answer was in the end, it would immediately get it, much more likely to get it. Right? So, well, here also there's a little bit of an issue because there was a problem of lost in the middle. Namely, it wasn't giving enough attention to tokens which were in the middle of a very long context window. Most of those issues have sort of been resolved. Nevertheless, this benchmark remains. So they put it at 5 different depths. So 0 depth means you put it in the first sentence itself. 25th percentile, 50th percentile, 75th percentile, and 100 at another tail end. Right? So these are the different places that you put it, while placing other distracting needles randomly. So what you do is other needles, distracting needles, you put all over the place, like you throw in some numbers or other things that can distract it. Each combination of depth and length is evaluated using 50 samples. So you do quite a few iterations. The average accuracy is reported. In other words, average accuracy over those 50, I suppose. Let n denote the total number of number city pairs and R the number of query cities. Like, for example, in the query, you can say, give me the magic number for San Francisco and Fremont, for example. That would be R is equal to 2. Right? And let's see what the results say. What it finds is that n is the number of needles, right? Number of needles that you insert. Okay? And R is the number of queries or cities that you're asking for in the query. So, and you give it a pretty reasonable context length, 4,000 tokens, and you see what it is. What you notice is that when you have only one needle and you ask for only one city, transformer and this, they do similarly. But the moment you give it 2 cities, now it has to remember more and search more places because there are 2 different needles. It begins to, you notice that right away, now this performance gap here begins to show through. This gap begins to show through. Then if you give it 4 needles, but you ask for 2 cities, then obviously now there is a lot more information and you have to have a very high signal to noise ratio to catch the right thing. You can see in this one, that already there's a substantive gap now. It's not a small gap. And by the time you put 6 needles, you notice that there is almost a 30% gap in accuracy. This is a substantial improvement. Right? So this is what they're saying. Likewise, you can do it with much longer context length. So that was with 4K. Now, if you do it with 64K, the results are actually similar. What they say is, as shown in figure 5. So let's go to figure 5. So let's go to figure 5. This figure needs explaining. See, look at 64K. And let me circle this. This is at 64K at different depths, like 0, etc., etc. Pay attention to this and attention to this for the depth transformer. So we are going to compare element by element. You would see that there is like a huge difference. The average is, again, here it is only 52% and here it is 83%. If you recall, that was pretty much the gap we were seeing even for 4K token length, and for 64K token length, it's even more pronounced actually, by a little bit, just a little bit more. But look at what happens to individual values. If you put your needle, the correct answer at the beginning of the sentence, at 64K length, a typical transformer, a standard transformer, its accuracy is horrible. It's 0.04, 4% accuracy. On the other hand, this has 60% accuracy, right? If you put it, and we know that, see, if you remember long ago, RNNs had this issue that they would remember much better the tokens that come towards the end than the tokens in the beginning. Transformers don't quite suffer from that, though there is a small sort of a bit of that, I suppose, residual bit of that still present. And so you see that if you put it at 25th percentile interval, then here it is 0.12, here it is 0.88, 0.7 versus 0.92. If you start putting it towards the end, it begins to quickly saturate. You notice that it begins to saturate. And it turns out that if you put it towards the very end, even a normal transformer gets it right always. And so does the depth transformer. So the most pronounced gap are in the beginning stages. If you notice that in the beginning stages, the gaps are pretty pronounced between the two accuracies. So in other words, it handles long context windows much better than a regular transformer. So the other thing is this outlier problem with attention scores. So attention outliers is not really a desirable, well, no, not this. This is not the attention. This is a basics attention analysis. So this is different, sorry. Attention score allocation to answer spans and noise context in the key information retrieval task. The target answer is inserted in varying positions. So the question is, if you put that needle again at those different 5 places, how much attention is that needle getting? And you can clearly see, and that was the whole point of this paper, that look at this. You would agree that it is almost a 10x, almost 9x improvement, 9-fold increase in attention between the regular transformer and the depth transformer. Right? Pretty substantial. Here it is about 10-fold increase, 10-fold. This is a little bit less. As you go towards the end, this traditional transformer begins to do a little bit better, but nevertheless, it is still 4 times better. And here it seems to be approximately 4 times better, right? So, and how much is the transformer paying attention to noise? Well, significant amounts. It is paying attention to noise. So that is the main point of this. Likewise, in context learning. In context learning is, if you give a lot of samples of data, Many short in context learning means you write your prompt, and in the prompt you give a few examples, and then you ask the machine, the LLM, to learn from those examples. It's literally learning from the information within the prompt to make, let's say, classify or make predictions and so on and so forth. So that is many short in context learning. So what you notice is that the diff transformer consistently does better. Look at this. It consistently does better by an average of 18 points in accuracy. Right? Likewise, and these are different benchmarks with 6 classes, etc., etc. But wherever you look, the one thing that's clear is that the diff transformer seems to be maintaining a fairly high degree of accuracy and leading over the traditional transformer. That is one. The other thing, which is more important, which I thought was actually, because I've sort of known the pain of this, is that suppose you give exemplars. Now what happens in your prompt, uh, what happens is that the order in which you give exemplars, the performance of the transformer is affected by it, right? So imagine that the only change you made in your prompt is that you change the order of the exemplar. And then you notice that now your transformer's ability to make prediction has gotten drastically changed, which is what you can see when you look at the accuracy. The same exemplars are being given, but they are going through permutations. And let's look at this. Robustness evaluation of in-context learning on the TREC dataset. Accuracy is evaluated with order permutation of demonstration examples by sweeping random seeds. Well, sweeping it just basically means that the results should be reproducible. But the main point is order permutation. As you change the order of the exemplars, you'll notice that, see how much this fluctuates. You see the band, there's a 19-point accuracy gap between the best performance and the worst performance. And that is annoying, that's disturbing, right? You feel that your LLM is it's like fragile, it's hypersensitive to small details, unnecessary or irrelevant details of your prompt, like the order in which you presented the exemplar. It shouldn't be like that. And whereas if you look at the diff transformer, and this is a very interesting thing, and we need to think how it achieves this. We'll try to understand that a little bit later. What you notice that the accuracy remains within a fairly narrow band of 4%. And this is quite a thing. You're getting a much more robust model using this approach. Right? And the results are similar if you do this. Examples are arranged alternately by class. So suppose you're writing a classifier between a cat and a dog. So you put a cat exemplar, then a dog exemplar, then a cat exemplar, then a dog exemplar, and so on and so forth. And then you ask a machine, okay, here is something. What is it? Is it a cat or a dog? Let's take a classification problem. That's what it means, that alternate by class. When you do that, once again, you notice that in those situations, the traditional transformer does horribly. Right? It's a bit of a known thing that when you interleave it like that, the performance of the transformer now goes 56 points variation between the best and the worst performing order of worst performing uh, studies. And this also suffers, actually. I would say that it's not quite perfect, or maybe there is a scope for improvement in the diff transformer itself, because there is a 13.4% gap. While 13.4% gap in accuracy or fluctuation in accuracy is worrying, nevertheless, it represents a significant improvement over the traditional transformer. That's the point they're making, robustness to in context, right? The other problem, which is quite interesting, and we should reflect on how this happened. See, it turns out that if you can cut out the noise and if you can pick up the signal, which is what this architecture will do, and we'll see why it does that, then what happens is it turns out that hallucination, it impacts the hallucination aspect of our LLM. As we all know, LLMs tend to hallucinate. So when they produce token, for example, there are many studies that show that the token confidences start falling down when it starts to hallucinate, and many other things happen. So one may plausibly argue that it's because it's beginning to pay attention to uh, not really relevant pieces of the tokens in the context. Right? It may be so because if you look at it simply by noise suppression, hallucination is impacted, which is quite interesting. That this approach contributes to differences in hallucination, right? So look at this. All of these, hotspot QA and all of this, these are not uh, like, I mean, it hasn't quite achieved perfection, but nevertheless, it represents a substantive increase in accuracy or free of hallucination on text summarization and question answer subsets, which is very nice. So it seems to bring many benefits. Generally, the model performs better, then it is more robust, and it has less hallucination. So far, we have seen three great benefits, right? And of course, it requires fewer tokens and fewer parameters smaller models can do. Right? The other is that this outlier activation problem. We don't want outliers, and outliers have impact on a lot of things. So now look at this. In a regular transformer, and I'll just focus on one line itself. Attention logits, the top will be 318 value, whereas the diff transformer has a much more muted thing. And internal hidden states also in the transformer, like after the layers and so forth, the feed forwards and so forth, I suppose. I'm guessing that's what it means, is also lower. So it's quite nice that you have managed to, while in the process of all of this, suppressed this problem of activation outliers. So I'll just read out this paragraph here. In large language models, a subset of uh, activations manifests with significantly larger values compared to the majority, a phenomenon commonly called activation outliers. The outliers result in difficulty from, well, okay, it also leads to model quantization, because if you're quantizing model and you're looking at the min and max values that you have to take care of, obviously imagine that you're doing, I don't know, 8-bit quantization. And we often do, like even if you do equal quantization or you do norm quantization, in any one of these situations, uh, you have to look at the range of numbers before you quantize. And the smaller the range of numbers, the less the more efficiently you can use your bits. Okay? So we demonstrate that diff transformers can reduce the magnitude and therefore, and as you can see, the accuracy, it manifests itself. As you know, transformers, the more you quantize, the worse the accuracy. But the interesting thing is that this line, if you notice, which belongs to the diff transformer, is holding itself up fairly well. Up to 6-bit quantization, you don't really see a degradation in accuracy, which is very interesting. Whereas at 6-bit, the normal transformer begins to cascade down. 4-bit transformers, which is what many of us, we tend to download because we don't have very big GPUs on our workstations. So there the accuracy gap is quite dramatic. 4-bit for a normal transformer is almost at 1/3 the accuracy. You know, the accuracy drop is 70% of the accuracy is lost. Whereas here you retain, well, not perfection, but you still retain 60% of the accuracy of the unquantized model. Right? So that's quite nice, quite a nice thing to observe. And so forth. So the ablation studies, they found out. So one of the things is there are certain hyperparameters in the model, and we'll talk about that and what those hyperparameters are and how do they affect the machine. So one of the ways, now let's get back to the mathematics and try to understand why it works. So just to summarize, where are we? We saw the claim that diff transformers, they address a core problem, namely that attention noise is there, and it leads to the transformer getting distracted in some sense. And let's go to the very first sense. Yeah, transformers tend to over allocate attention to irrelevant context. Basically, it's saying that why is it listening to noise? Right? Let's remove that. And when you remove noise and you filter it out, how does it affect the machine? And the main thing that you notice is that a process of filtration does lead to improvement on almost all fronts that you think about of in a transformer. Right? So far so good. The experimental results prove it. The whole question is, how is it able to filter? Like when you look at this diagram, when you look at this diagram too, and you think of your typical, you're tempted to think of your typical differential amplifier, X1, X2, you realize that something like this must be there. You are trying to do a delta. So your basic intuition should be that somehow for the answer, for the needle that you have hidden in the haystack, for the answer, that those pieces of text that do answer the query, somehow that delta should be significant. Whereas for all other pieces, all other tokens, the delta should be close to zero. In other words, they're suppressed, right? The difference between these two values should be very, very small. And so fundamentally, there is a pull-push mechanism built into this equation. So, and the way to look at it is, I'll interpret it like this. In the appendix, they go through the math, and they don't specifically address it, but it took me quite some time to reason through and see how it is happening, and then it does become evident once you carefully work through the math. When we do that, actually, it is quite straightforward. So in the appendix, if the last appendix that you see, the gradient flow of diff transformers, because that is the most important thing. The whole question is, how is it that when you use a diff transformer as opposed to a normal attention by using two different softmax, why is it able to somehow do noise filtration? That's the main question, right? The fact that it does it is very good, but how did it all work? That's the question. So let's look at that a little bit carefully. When you grind through the math, it's fairly straightforwardly explained, but let's look at any one thing. If you look at this, let's say the loss with respect to WP. This is the loss sensitivity to W, the first key, the key matrix, key one matrix. And this is the same thing with WK2 matrix. Right? So observe something very interesting, that this one has and I'll just highlight it because that is what helped me understand. You notice that there's a 1 over square root D, which is also here. But instead of 1, you have 1 minus lambda. Right? So they are, in a way, pulling in opposite directions. Lambda is a positive constant. It's a learnable factor, actually, a parameter, but we'll leave it there. What it is doing is, it is saying that the machine now has, when you learn that the way the gradients will flow will be such that for signal, for the answer, for the tokens that matter, when you backpropagate the negative log likelihood loss and so forth, the machine will be forced to do this. For signal, it will have to, the score function, remember the S1, S2 score function, that we talked about, let's go up here. Let's look at this. So I'll just talk of the score function 1 and score 2, right? So this is your basic equation. And the loss function, basically what it has to try to do is that for tokens, for important, relevant tokens in the context, think of it as the input sequence. What it has to do is this delta, a score, delta score, it has to spread it out. There is a push them apart, delta score. Push the two you can, and it's learnable. The fact that when this machine is forced to do loss minimization through backprop and gradient descent, it has no choice, but for relevant tokens, it will have to get a good loss function, a loss value, low loss or minimized loss, it will have to do its gradient flow in such a way that this delta is maximized for signal, right? Push the two apart to maximize delta score, right? So for example, it could do it by boosting up the score 1 function and boosting down the score 2 function, right? And for everything else, for noise token, it has to do the opposite. It has to pull these two scores together. So delta score needs to be very small, ideally 0. And so what it will do is it will basically learn to know that these tokens don't matter. So it will learn to suppress the delta between these two. And that is the way, that is the mechanism by which this using two softmax heads comes in useful, that the gradient flow gets a chance to maximize the difference between two score functions, two softmaxes or two score functions, when you have a relevant token, set of tokens, and minimize it for all the rest of the tokens. And that's sort of the mechanics of why or how this thing learns during the learning process. You can train this transformer to do what it is doing. So this is the way I understood the paper. So this is all I have, guys. Are there any questions? Was it clear, guys? Was the explanation reasonably clear? Or did it make sense? Everyone is on mute. So I'll assume that there are no more questions. So this is it. This is this paper, Differential Transformer. I think it's a very good work, and like a lot of very good work, it is based on a simple idea that seems to be very effective. And let's see how well it stands the test of time.